Hello, Mr. Farley. I hope you're doing well. This is section 13 by ET and J-Rod. So today we're going to talk about the theory of matter, and I'm going to tell you guys a little something about atoms. Okay, in Greek, atom means indivisible. This makes sense because everyone knows that an atom is the smallest molecule. All right. Uh, Next, we're going to talk about Brownian motion, which is a discovery about the movement of atoms. Named after the Robert Brown and his observations back in 1827. Okay, my guy had a distinguished idea to put pollen grains in water, all right, and then stick them under a microscope to observe them. What he found was that to the naked eye, the water seemed to be perfectly still. But under the microscope, he saw that the pollen grains, which are, well, microscopic, were moving around in very erratic ways. The atomic theory supports this discovery because we see that the atoms of any substance are continually in motion. All right, next you see on the slide that a typical atom is around 10 to the negative 10 meters in diameter. That's substantial. That means that 100 million atoms placed right next to each other are still as tiny as 1 centimeter. If you don't know how much 100 million is, let me put that into perspective, okay? That would be just enough for me to pay to go to college. That's crazy. Uh, Now you may be wondering, how do we figure out that an atom is 10 to the negative 10 meters in diameter? Well, of course, my main man, Sir Albert Einstein, looked at the experimental data from Brown's experiment and just did some quick math. Simple as that. Uh, Famous Ray, I hope we're not boring you here. Please wake up. Thank you. Now, lastly, atoms, they be social distancing. All atoms are initially attracted to each other. You know, just like how we are all trying to go out and see our friends. However, when they come into close proximity of each other, like 6 feet, just kidding, it's way smaller than that. But when they do end up too close to each other, they start exerting repulsive forces on each other. This is very key to explaining why matter takes up space. Think of how water is pushing away from itself when it's inside of a container until it fills up the container. Yeah. In the end, they're always social distancing. And okay, J-Rod, uh, it's time for you to to help me out. help me.
All right, class. So now we're gonna talk about the the last two sections of the chapter we're talking about. So next we're gonna discuss what thermal equilibrium is, and basically it is said that if two objects at different temperatures are placed in thermal contact, meaning that they're touching each other, the two objects will eventually reach the same temperature. Now, as you can see in the picture to the left, if you take an object that's 100 degrees and an object that's 0 degrees, put them together, eventually the 100 degrees will lower down to 50 and the 0 degrees will raise up to 50 degrees. This is just what happens. And when these two objects reach the same temperature, no net energy is flowing between the objects. So there's no energy flow whatsoever because both of these objects are at the same temperature. So next, we're going to discuss the first law of thermodynamics. Just kidding, because what I'm actually going to discuss is the zeroth law of thermodynamics. Basically, they had to name this law the zeroth law because by the time this law was put into play, the first and second laws of thermodynamics were already present in the world. And basically, the best way I could explain this is very much like the transitive property. If you have two objects that are in thermal equilibrium with each other, and the system happens to be in thermal equilibrium with a third object, then all three of the objects are in thermal equilibrium with each other. So basically, A is equal to B is equal to C, in other words. So who knows the answer to this question? What happens to Pinocchio's nose when he lies? You can pause this video to think about it, even though most of you may know the answer. And also with this question, what happens to his nose when he stops lying? Again, pause the video at your will. So something similar happens to substances when they are heated or cooled down. Similar to how Pinocchio's nose lengthens and expands when he lies. This is sort of like thermal expansion. So pretty much when certain objects are heated up, they expand in length. Depending on what the object is, however, there's a different rate of expansion. So linear expansion can be described by the equation, the change of length is equal to alpha, which is the coefficient of linear expansion. As you can see to the picture, in the picture on the right side of the screen, there are two rows on the right side of the diagram, and the first row represents coefficients for linear expansion of all these objects. So you take the coefficient, you multiply it by the original length of the object, and also by the change of temperature, because this is how the object is expanding, is being heated up, is being cooled down, shrinking, etc., etc. But there's also another side to thermal expansion. There's also volumetric expansion, and this equation is very similar to linear expansion, except instead of changing length, now you're changing volume. And also, it's also different because there's a different coefficient that you use. Instead of alpha, it's beta. And you could direct your attention to the circle on the left side of the screen. And these are all the numbers you're going to be using for equations using volumetric expansion. And of course, depending on the material, for example, aluminum, copper, gold, all of these materials have different rates of expansion. So depending on the question, you're going to have to use different coefficients. And that's all I really got to say. So hopefully that was helpful. And Jeff Train, I'll leave it up to you.